Welcome to solverfy.
Okay, so we're in chapter 22, problem 43. So a very large, assume infinite, flat slab of non-conducting material has a thickness d and a uniform volume charge density, positive rho e. We want to show that a uniform electric field exists outside of the slab and determine its magnitude and direction. So first we can choose a cylindrical Gaussian surface with the flat ends parallel to and equidistant from the slab. By symmetry, the field must point perpendicularly away from the slab, resulting in no flux through the curved part of the Gaussian cylinder. And by symmetry, the flux through each end of the cylinder must be equal with the electric field constant across the surface. So what that is saying is the electric field dotted into the surface integral of our Gaussian surface is given by 2 times the magnitude times the area. Awesome. So now we have to set this equal to the charge enclosed over epsilon naught, as Gauss's law says. So what is the charge enclosed? So this is given as our surface area, or surface charge density, the volume charge density, rho e, times how much volume we're enclosing. Well, the volume we're enclosing is E, or not E, A, the area, times the thickness of the slab, which is D. So if we plug that into our equation up here, we can then solve for what E is and see that this comes out to being rho E D over 2 epsilon naught. And the areas cancel out, so it doesn't really matter how we draw our Gaussian surface. So that's very cool. And also, the electric field is independent from the distance from the slab, which is also interesting. Okay, part B now. This is the more challenging part, and it says, as shown in the figure, the slab is now aligned so that one of its surfaces lie on the line y equals x. That's what's shown here. Line y equals x. And at time t equals 0, a point-like particle of mass m and charge positive q is located at y naught, point y naught here. Cool. And it has an initial velocity of v naught in the positive x direction. We want to show that the particle will collide with the slab if v naught is greater than square root of root 2 q y naught rho e over, or d over epsilon naught n. That's all in the square root. If v naught's greater than that, then it will collide. And we're ignoring gravity. Okay, so this is going to be tricky because we have lots of coordinate system stuff to think about. So when the coordinate system of the problem is changed to axes parallel and perpendicular to the slab, it can easily be seen that the particle will hit the slab if the initial perpendicular velocity is sufficient for the particle to reach the slab before. Okay, so what we're going to do is we're going to rotate our axes. So now this is our y-axis, our new y-axis, which I'll call y prime, and this is the new x-axis, x prime. So these get rotated an angle of 45 degrees. Okay, so in the new coordinate system, we can do some transitions here. So initially, I'll write in black for the old coordinate system. We have r naught vector is y naught j, and v naught vector is v naught I. So now let's write out our vectors in the new coordinate system. We have our r naught in the new coordinate system to be y naught cosine of 45 degrees r hat plus y naught sine of 45 degrees z hat. Okay, so we can also transform the velocity vector to this rz basis, with r being the perpendicular basis and z being the parallel basis to our slab. So our v naught thus becomes negative v naught sine 45 degrees r hat plus v naught cosine 45 degrees c hat. And lastly, our acceleration vector, since in this basis it's very easy because we know it's all radial, and the force is given by QE, and then to convert to acceleration, we divide by mass, and this is radial, so in the r hat direction. So now if we want to find just the perpendicular components, that is given as v naught r, and what we can do here is insert this into the equation to find, or it says equation 212c, so this is old mechanics stuff. So we have 0 equaling r vr squared minus 2a over r minus r naught and this equals v naught squared over 2 minus 2q over n rho e d over 2 epsilon naught, just plugging in what our e is for our acceleration here. And now we just plug in the differences in r vectors, and this is y naught over root 2 minus 0. Cool. So just as a set again, so this is the initial velocity in the r direction squared minus this, and this equals the final velocity. But we're setting the final velocity to 0 because we want to see if it will even reach the slab. So to see if the velocity will reach the slab, we then solve this equation for v naught. So let's rewrite the equation down real fast. So this is 0 equaling v naught squared over 2 minus 2q over m. And now we write what E is. E is rho e d over 2 epsilon naught. And we have our r vector. Our r vector is y naught over square root of 2 minus 0. Cool. So now we can just solve this for v naught squared. And this over 2 equals 2q over m rho e d over 2 epsilon y naught over root 2. Cool. So now v naught squared equals cancel these guys out, and this equals 2 over root 2 q over m rho e d y naught over epsilon naught. Cool. And that's the same as root 2 q rho e d y naught over epsilon naught m all square rooted equals v naught. And that's exactly what we wanted to show. So this is the exact initial velocity it would take to stop exactly on the slab. So if the velocity is anything greater or equal, oops, I did that the other way. If the velocity is greater than or equal to this value, it will contact the slab.